So thank you, vielen Dank. So maybe I mainly speak English. I could do it also in German, but someone would not be so happy. But I thought I would read some shorthand. So now this project began in 2018. I got an enormous amount of money from the European Research Council, which philosophers very rarely get, for telling posterity what secrets can be found in Gödel's shorthand notes. Now, the incompleteness notebooks are, of course, the sort of first thing to do, a real must, which I also did. This was also published already last year, but it's still perhaps interesting to see how the originals look like, and maybe something new can come out from this presentation now. So let's just proceed. Oh, here is, you see young Kurt Gödel, very handsome, somewhere in Vienna, I suppose. He kept all things he wrote down, and he was also compulsive in writing down things. He would even just write down things to calm himself down. So just he could do like arithmetic computations as a form of taking it easy, of relaxing. Now, this is Gödel's zeroth theorem here. 1 + 1 is 2, then corrected. So, I mean, he just kept his school notebooks and had them sent to the United States sometime in the 40s. Then, when you study Gödel, you encounter all sorts of handwritings, not just this little boy's, but at the age of 9 or so, then he had to switch his handwriting into the Zitterlin-Schrift, and you see how enormously regular and decent it is. It looks printed like Aufgabe. I happen to have learned Zitterlin at the Deutsche Schule Helsinki. I forgot that I had learned it, but then it was sort of easy to learn it again. Ich turne, ich turnte, ich hatte geturnt, and so on. So this is one thing you find. Here is a page from a notebook which has Gabelsberger. The first word is Frage and so on, and has this fancy wavy drawings. This is from the time when Gödel began his studies of logic and foundations, which was about May and June 1928. He was following Rudolf Carnap's Logistikübungen in Vienna. Now, one of the Logistikübungen that Carnap gave was to formalize arithmetic. And so you have this thing in which it is written Übungsheft log. And then the keen eye notices at once a Hilbert Ackermann notation. Here you see, for example, for all, now here you have AX, so that's the capital Zitterlin A. And then you have for all x AX, and this is just now how you derive the sort of plain rule of generalization from the Hilbert Ackermann rule of generalization, which is that if you have an implication like here, then you can add the universal quantifier if the eigenvariable lowercase x is not free in the antecedent. So he shows that this. Now, this was classified among his school notebooks by John Dawson as of year 1922 or 23. And I was, of course, enormously lucky to have found it, and saw at once that this is now Hilbert Ackermann, so book that was published in 28 can't be 22. The upside down notation is the same kind of notation that, you know, these things here, like that you have in Carnap's Abriss der Logistik that was published in 29, and that Carnap was preparing in 28. Anton Dvoryanki. Sonnenfeld Anton Dvoryanki is a place, so that's some friend of Kurt's. We don't know. Anyway, now this Übungsheft Logik is quite an interesting thing. On page 14, the formalization of arithmetic has come this far. Can you see the sort of, when I show like this, Can you see the hand? You see the cursor there?
Yes, it's
good.
small, but
Now, yeah, good. So now I can then read. So for all first order properties, the property is erblich, so hereditary, if and only if, so definitional equality. For all objects x and y, if x has this property, if y is x plus 1, so in a relational language, then y has this property. So that's the property of being a hereditary thing for natural numbers. And for x is a natural number means that for all hereditary properties, if one has the property, then x has the property. Now that's like making induction part of your theory of natural numbers. Then the first task is to show that 1 is a natural number. This 4 stands for Voraussetzung, so condition, like in Hilbert and Ackermann. So you assume that you have a hereditary property, you assume that 1 has it, and so on. And then you come to prove that on the next page that 1 is a natural number. But let's look at the second proof here. Now you assume that A is a natural number, that B is A plus 1, and then these A and B are written here because they will be eigenvariables in a universal generalization. Next, you assume that P1 is a hereditary property and that 1 has it, and that's also signaled out as an eigenvariable. Then you apply some definitions, and like here you see you have this implication, you have its condition here, so by implication elimination you get this one here, and so on. And so in the end you have proved from this assumption that P1 is a hereditary property such that 1 has it, that B also has this property. Then you introduce the implication and generalize at the same time. So it's a linear natural deduction system, just like the Fitch system. And there are no sort of annotations as to which rules are applied. So you have to figure out the rules from the way they are written. Implication elimination, implication introduction, generalization, and so on. The next thing he proves, he assumes that A is a natural number and B is a natural number and C is the sum of A and B, and these are now the eigenvariables. Then he just goes on for 4 pages like this, you see, maybe here, yes. So then you get that C is a natural number, and then you just get rid of all the assumptions, and you have that for all x, y, and z, if x is a natural number, if y is a natural number, if z is the sum of x and y, then z is a natural number. So natural numbers are closed with respect to addition. This goes on for 40 pages. It's an impeccable system of linear natural deduction. Then he starts to do similar things with set theory, which was also one of the Logistikübungen that Carnap had given. You have to formalize set theory. I thought first that this would be Schröder, that looks like Schröder notation, but it's the notation from Frenkel's 10 Vorlesungen über die Grundlagen der Mengenlehre of 27. So the subset relation is written like this now. If P is a subset of an empty set, then you come to the conclusion that it's actually equal to the empty set. And then you close the assumption, this assumption here, and generalize with respect to this P here. So for all classes, if they are subsets of the empty set, then they are equal to it. And so this goes on for 20 pages or so. Now, in some completely different quarters, 4 years later, this thing was written down. This is Gentzen's shorthand, and it's not the old Gabelsberger shorthand that Gödel was writing, but it's the later Einheitliche Kurzschrift. And now I am always a bit nervous and sort of worried when I have to encounter Gentzen's, because it's different, but I more or less figure out what it says. It says 5 verschiedene, I think it's a Formen natürlicher Kalküle, so 5 different forms of natural calculi. Serie PLF, it's like a series Prädikatlogische Formen. Something like this. And this is written in September 32. Schlussschemata, you see the standard rules of natural deduction here. And it's even classical because you have the rule of indirect proof here. And then a few months later, Gentzen had figured out the conversion schemes of natural deduction. So if you, so it's like und Einführung. So conjunction introduction, you conclude A and B, and then you apply und Beseitigung. You conclude A, then it says here in Sütterschrift, wird zu, and so that's the conversion. And of course, like say with implication, you assume A and then there's some gamma derivation of B. So you introduce Folgeeinführung, A implies B. Then you eliminate it. So this becomes now this converted thing. And this was written like maybe late 32 or so. And then sometime early in 1933, Gentzen proved normalization for this calculus, for the intuitionistic calculus of natural deduction. Now it's written in a normal way. I don't know why. Dissertation. I found this thing in 2005. I consider myself still enormously lucky in having found it. And this is a detailed proof of normalization for intuitionistic natural deduction. Now, Gödel did not think about natural deduction as a logical system in its own right, but he just wanted to use it for formalizing proofs in arithmetic. That you cannot do in axiomatic logic. It's impossible. But so then he invented natural deduction for the purpose, which was not bad, but he just didn't stop to think about its properties, contrary to Gentzen, who then figured out the normalization result and then did the corresponding cut elimination result for classical and intuitionistic predicate logic. Now, so Gödel put that problem, it sort of didn't see that problem. He then proved the completeness of predicate logic. I now know that he did it in December and January. December 28 to January 29, he had done the proof. Then he wrote it down in February or so, 1929, and sent it to Hahn and so on. Then what he did from 29 to 30, the academic year from 29 to 30, I don't know. He seems not to have done anything special, but something was growing in his mind. He wanted to extend the proof of completeness of predicate logic to higher order logic, and for that he needed a truth definition. And then at some point in the spring of 1930, he realized that something is seriously wrong with this idea of proving completeness for higher order logic. And how this went, I will try to show to you through documents. But let's first look at the top of the typewritten version of Gödel's famous article. As you see, there's no like part one. There's a footnote here, but there's no part one here. And then this famous opening, die Entwicklung der Mathematik in der Richtung, and so on. This is how the final version of the incompleteness paper in shorthand looks like. So it says Arbeit, unrein, so draft. And this famous, it's quite close to the printed version now. I'll read to you some of this. Die Entwicklung der Mathematik in der Richtung zu größerer Exaktheit hat bekanntlich dazu geführt, weite Gebiete von ihr, then cancelled, der Intention nach die ganze Mathematik zu formalisieren. In der Art, first it was Weise, then Art, dass das Beweisen nach einigen wenigen mechanischen Regeln vollzogen werden kann. I learned German as a child at the Deutsche Schule Helsinki, and it's remained like a a child's German. So in shorthand, the grammar is not so, if it's there or D, you don't see it from the writing. You have to know it, and I don't always know it, and so on. So it's not like you could figure out the grammatically correct German text just like that. But you transcribe, and then someone who has an adult German will fix the if it's there or D and so on. But it's sort of it's something that when you translate it into English leaves no traces, this sort of reading. Now it goes on. D. Now you don't know, usually you don't know if it's plural or singular, so you just think, well, it's one or the other, and we'll see in the end if it's plural or singular. Die umfassendsten derzeit aufgebauten formalen Systeme sind das System der Principia Mathematica, einerseits das Zermelo-Frenkelsche Axiomsystem der Mengenlehre. So you see, usually names should be written in longhand, but Gödel doesn't care about that. Anyways, so this is how it looks like. And even the footnotes, as you can see, they are an integral part of the planned paper. It's not in a good shape. I had to go to Princeton to unfold these corners and read what was hidden there. So this is from the microfilm. Now, how did he come to this result? Here is a summary of Gödel's of Hilbert's talk at the International Congress of Mathematicians in Bologna in 1928. This talk gave 4 problems in the foundations of mathematics. Probleme der Grundlegung der Mathematik. Now it says, Vollständigkeit des Axiomsystems der Zahlentheorie. Das heißt, es ist zu beweisen, this is a Sütterlin capital S, S und Negation S nicht beide als widerspruchsfrei erweisbar. Wenn es widerspruchsfrei ist, so ist es auch beweisbar. And there's this addition. In welchem Sinn darf die Induktion im Widerspruchsfreiheitsbeweis angewendet werden? Okay, so here was the problem of proving the completeness of number theory. Then this is one of Gödel's library slips. You see, this is the Frenkels Einleitung in die Mengenlehre, the 28th edition, and this here is like 5th of April 1930. So he took it out, and this is what you read there. Frenkel discusses Skolem's paradox, that if you have a formal syntax, then you can enumerate your propositions, and likewise theorems will be a subset of those. And then there's this passage. It is a fact that until today no mathematical problem has been proved to be unsolvable. The discovery of such a problem would be without doubt present an enormous novum for mathematics, and not only for it. Now, this of course happened, as we now know. Then there was another early influence. This is from the 11th of May 1930, and this is the awfully long 49-page long paper by Skolem, published in this Vetenskapet, it's all written wrong. This is Norwegian. Vetenskapssällskapets skrifter. Finland is bilingual and Swedish is my mother tongue, so Norwegian is just the dialect of that. Anyways, so, and there you have things like this. There's this idea that you can put all things in lexicographical order. Skolem is repeating it all the time. properties of natural numbers you cannot put in lexicographical order. Then he says in the end of this paper that it would be an interesting task to show that every collection of propositions about the natural numbers formulated in first order logic continues to hold when one makes certain changes in the meaning of numbers. Now, the first order logic, that may be, in the original, it's probably Zählaussagen. That was the sort of name of predicate logic in the 20s. So first order quantifiers. This was 29, so poor Schoolem, he should have pursued this interesting task, which he didn't. Now there's again a summary of Gödel's, of this Schoolem Skrifter, citiert Kongress Helsingfors. This was Helsingfors is a Swedish name of Helsinki, so it was a congress in which Schoolem was speaking. So paragraph 2, Beweis des mengentheoretischen Relativismus, insbesondere ein Axiomsystem aufgestellt wird, in dem sämtliche Konstruktionsprinzipien für Mengen als Grundoperationen genommen werden. Okay. And the interesting part is perhaps here. Oh, yes. This is just some transcription that I did of this. I used to do it by hand, but now I do it on the computer. Now this is interesting. Yes. The last part of Schoolm's paper. Beispiel für einen Bereich, der nicht mit der Zahlenreihe isomorph ist, obwohl ein int-Bereich, so integral domain, I think, integral, whatever, und obwohl für je zwei relativ prim HK Disequality. Vermutung, dass die Zahlenreihe überhaupt nicht durch Zählaussagen charakterisierbar. So, conjecture that the number series is not at all characterizable by first order propositions. So here's another time that Gödel took the same paper of Schoolem's out. He was in Berlin after the famous Königsberg meeting on foundations of mathematics in the beginning of September 1930. So then you see that, you can even see that he was staying in the Hotel Prager House. And so I was reading this again. Let's see, yes. Oh, this is just the same page. Now, the incompleteness paper explains the result in a certain way, but once Gödel was sure that he was taken seriously, then he would explain in a much more intuitive way how he how you get to incompleteness. And these are his notes from a talk, or a sort of a typewritten version for a talk that he gave in Bad Elster in September 1931. So then with this idea that you can put propositions in a lexicographical order, then you can also do put in such an order all first order propositions that have one number variable. So you have the first and second and so on. So you have this denumerable sequence of properties of natural numbers. Then a class K of natural numbers is defined. Now he has by this time arithmetized the provability predicate. So it is not provable that the nth number has the nth property in the sequence. That is that defines a class of numbers K. Okay, and then of course you have to find this property somewhere. This property somewhere in the series of properties of natural numbers. So this not Bev and so on, it must be some kth property of natural numbers. And then you just diagonalize, you put in place of n k, and you say find that this phi kk says that I am not provable. Then assuming that the system is consistent, says, aus der Annahme, dass bla bla sei beweisbar, würde folgen, dass bla bla richtig und daher wegen für nicht beweisbar wäre. So the only conclusion is then that this is unprovable. And this was his sort of a way of presenting the result from when he had it accepted. I will be rushing a bit, so if I have 20 more minutes left, can't remember why I wanted you to see this page. Anyways, the pages look like this. Took a lot of work to read them. There are many versions of the paper. This is sort of a summary of what you have there. These are, by the way, these are just frame numbers in the microfilm reels. So frame 339 right side and so on. This was his sort of series of, well, I'll put them all here. So this is sort of my list of contents for what you find there. Then he has Aleph naught consistency. And seventh is that the central theorem is that all provable formulas are true. Okay. Now you see, now I will read you a bit from here. Man überzeugt sich leicht durch vollständige Induktion von der Richtigkeit des Satzes. Jede beweisbare Formel ist wahr. Da offenbar die Axiome wahre Formeln sind und diese Eigenschaft durch Schlussregeln nicht zerstört wird. Allerdings kann dieser Satz nur mit Hilfe des Auswahlaxioms bewiesen werden. Okay, so his idea until September was that he proves a meta-theorem about the Principia Mathematica, namely that all things provable in the Principia Mathematica are true. And for that, he needs some sort of a truth definition. And then, as you just heard, then it's easy to prove by complete induction that all provable things are true. Now, this is, of course, but you need the axiom of choice for this. This is, of course, something that you never heard about if you, before these were transcribed. He didn't tell anyone that he put it in this way first. So why was it changed? Now, there's a second set of notes. These notes don't have any dates, but here you have a sketch of the Königsberg lecture on completeness of predicate logic in the middle. So we know that whatever was written before that was before September. And it's this kind of a plan of contents. The concept of truth, and then proof of this lemma that all provable things are true. Then von Neumann discussed with Gödel these things, I think also in Berlin afterwards. There are some things that von Neumann knew, which Gödel found out only after Königsberg, so right after. So the set theoretic notation fell away and omega took the place of Aleph naught. And then he wanted to do a sort of syntactic approach in which this sort of a contentful correctness, inhaltliche Richtigkeit, applies only to recursive formulas. So as I write here, the truth definition just simply disappears. He doesn't talk about that kind of things at all. So the approach to incompleteness was completely revised after the encounter with von Neumann, from a set theoretic approach based on the theory, some sort of an idea or concept of truth, to this kind of a very sort of nominalistic approach in which you don't assume much. Let's see. Now, this is then about the second theorem. Consistency is the assumption by which the meta-mathematical proof of an undecidable formula Well, that's an incomplete phrase. Let's just read what he says. If one could prove the freedom from contradiction of the Principia Mathematica within the system, then one could even prove not something which is in contradiction with the undecidability of this problem. From this follows the strange result that one cannot carry through a proof of freedom from contradiction for the Principia Mathematica, even with all the logical means contained in the Principia Mathematica. So that's, of course, the second incompleteness theorem in a certain way. Okay, this was already so. Now, so this is the first page of the final shorthand draft of the article, and this is the last page, and it says, zum Schluss sei noch auf folgende interessante Umstand hinsichtlich des unentscheidbaren Satzes es hingewiesen. Hin is awfully bad. Hingewiesen. Yeah. And this is sort of an indication that consistency would not be provable, but it's stated in a very roundabout way. These are just footnotes. These are just remarks for the editing of the thing. Now, this is then 5 pages ahead in this notebook. Then there's this page, and I checked. The notebook is in one piece. It says, Lieber Herr von Neumann, besten Dank für Ihr Brief von. The date is missing. Ich muss Ihnen leider mitteilen, dass ich schon seit ca. 3 Monaten im Besitz des mitgeteilten Resultates bin. So von Neumann wrote to Gödel that in November, like about mid-November, that he has found a wonderful consequence of the incompleteness theorem, namely that the consistency of mathematics is not provable. And Gödel got this letter about 3 days after he had sent his paper for print. Now, we just saw the ending of the paper. It just said in a very roundabout way something about interesting consequences of concerning consistency. Then he had a very busy weekend, so he got this maybe Friday or Saturday morning. And then he had a very busy weekend in which he wrote like this kind of things, like if you know well Gödel's paper, then you recognize that these are the kinds of formulas that you have in the 4th and final section of that paper. Vid kappa implies not bev kappa 17 gen r and so on. And after the sketches of several pages like this, then there's another letter sketch, Lieber Herr von Neumann. Herzlichen Dank für Ihr Brief von, and then it's 20th of September, but this should be November. Gödel mixes 9 and 11 in Roman notation, I don't know why. And ich muss Ihnen leider mitteilen and so on. And then he cancels it and then. Das Resultat, von dem Sie mir schreiben, ist mir schon seit ca. 3 Monate bekannt. Then he starts explaining why he didn't say anything about this result and that it will be published in the beginning of 31 and so on. Now, let's look at the typewritten manuscript. This is I read to you this beginning, so this one I read to you. Zum Schluss sei noch auf folgenden interessanten Umstand hinsichtlich des oben aufgestellten blablabla. And then it goes on, but not here. So the next page looks like this. What happened? 41, 42. The thing is that Gödel wrote an additional section to his paper, and then there's a postcard by Hahn, which says that legen Sie bitte diese Seiten von der Arbeit von Dr. Gödel by or something that was to the printer that please attach these. So this is Gödel's, Gödel struck out this the beginning of his closing paragraph, and the original page 42 was well, dismissed with, and it was replaced with a new section that is here, and you have verbatim the kind of things that he was writing between the first and second letter to letter sketch to von Neumann. So over the weekend he wrote this additional section to the paper, and it was sent to the printers who made this modification. Then the proofs came, and as you can see, well, this is how I discovered this thing. I said, well, why is it not? Why is there not part one? It's sort of added here. And why are all the remarks about the second incompleteness theorem just in handwriting and in the last section? So nothing in the paper before, as printed here, as typeset here, nothing there mentions in any way any second incompleteness theorem. It's just in the additions, and then in the you see lots of additions here. This is the end of the introductory section, and then there's this incompleteness result is sort of added as an explanation. And then you come to the fourth section. Now, these proofs, they would have revealed Gödel's tricks, so he didn't show them to anyone. But then he got other page proofs, and then you couldn't see anything of this. And then those he kept then sending around. Well, there have been different reactions to this thing. One result of this is that von Neumann didn't publish his proof, and the proof has disappeared. Now, one reaction is, how stupid, now we don't know what von Neumann's proof was. Another reaction is, probably von Neumann's proof was as bad as Gödel's, because if you go and look at this Gödel proof of the second incompleteness theorem, it's a total fake, an absolute total fake. Look at this. So he takes this impressive looking implication, which said that consistency implies non-provability of this Gödel sentence. And he just says that the only thing that was used for proving incompleteness was this Tatsache. So this is now a Tatsache that he writes down. And then he uses a definition and another definition, modifies this implication a couple of times, and then says that, well, now it's proved. So nothing is proved by that. Anyways, so the second reaction was that maybe von Neumann's proof was as bad. A third reaction was, I would have suggested a joint publication. Fourth reaction is, dear Jan, why do you use your time for such trash? So this means that one should sort of, out of respect for Gödel, not say anything unpleasant about him, but it doesn't make this thing vanish in any way. Maybe there was some other reaction next to these, but anyways, there was of course never any second part to Gödel's paper. He was never able to prove the second incompleteness theorem to his own satisfaction. What it would have to be. There are some of his lectures from the early 30s, sort of popular lectures about incompleteness, and there he says quite clearly that the statement consistency implies the Gödel sentence. So it's, let's say this thing here. So consistency implies the Gödel sentence that this is provable in first order arithmetic. So that is what he tried to do. No one has been able to give such a proof as far as I know. And it would be a really interesting task now. Give a proof in Pano arithmetic that the consistency statement implies the Gödel sentence. That's a very clear task. But as he didn't manage to do it, he just then, when Carnap was asking him once, like 32 or 33, he said that, let me try to recollect. He said, yeah, the second part of my article exists only in the realm of ideas. Yes, well, now this was a formidable picture that I remember when I went to school and I read some book about Gödel. It was this horrible book, frightening looking man. Anyways, the whole story can be found in this book that came out last year. It's in English translation. I am open to anyone who is interested in trying to do a German edition of all of this, and I would help and give my German transcriptions for use and so on. But now, well, it's about time to finish. I think I used all of my time. Thank you.